Hello, everyone. Thank you for coming to the talk. My name is Vashisth Tiwari. I am a sophomore at the University of Rochester studying physics. And today I'll be talking about using machine learning to identify astrophysical transients in the DESI survey. I did this research with Amanda Wasserman under the mentorship of Professor Sergey Benzvi, who works on DESI collaboration. If you have any questions or comments, please reach out to me here. So just a bit about DESI. DESI stands for the Dark Energy Spectroscopic Instrument, and it's a massive redshift survey of 35 million galaxies and quasars. And it will map the large scale structure of the universe out to a redshift of 3. So during this survey, we expect to see a lot of transient objects like supernovae, tidal disruption events, etc., that can contaminate the spectra of the host galaxies. So you'll be asking, why is it important to identify supernovae? So the primary purpose is supernovae are used to ensure that the estimates of the redshifts of host galaxies are correct. But additionally, they're also used to obtain the spectra of transients themselves. And this spectroscopic classification is the gold standard in the classification because these discoveries can be compared against the photometric surveys, the data from the photometric surveys. So what we have done is we have developed the machine learning tools to identify and classify these transients in the galaxy spectra. And that's what I'll be discussing today. Sorry. Um, so I'm sure all of you have heard about machine learning, AI, things like that. I think the example that I like the most is using them to classify different cute animals like cats and dogs. So what we are doing here is essentially the same problem, but rather than classifying cats and dogs, we are classifying these supernovae. Um, and rather than using 2D array of images, what we have is 1D array of fluxes. So traditionally, the way we identify supernovae is we look at specific features. So for example, when you're talking about type 1a, you would look at the silicon peaks, right? However, the problem with this method is, one, it's computationally very, very expensive. Second, if the noise in the data is very high, so this is the sort of data we have, it's very hard to see these features, right? So what we are doing and how it's different from the traditional practice is we're asking the network to pick up the features things important, which it thinks are important, and then train on them. So we are letting the network essentially do the work. Um, so supernovae are very, very sort of rare events. So we simulate them using the BGS survey things. Um, and that's what is used for the training of the data. So you see, this is the data we collect, right? And it's very hard for the network to leech onto anything from here. So we need to pre-process the data in such a way that it retains the features, but still cancels out some noise. So the first thing that we do is weighted logarithmic rebinning of the data. So where we go from having 6,000 points to 150 points. And in the weighted rebinning, we use the inverse of the variance and things like that. Then you also see that this negative brightness here, which doesn't really makes a lot of physical sense, and it's because of the noise in the data. So what we do is we clip those negative values, um, and then we want to reduce the range from that goes from -30 to 40. So we normalize it between 0 and 1. Normalization is a standard practice in machine learning because it reduces the computational time and helps the network convert faster. And lastly, we de-redshift. So you go from having this hot mess to something that does have some sort of structure and a pattern that network can learn on. So each of these classification problems require a different architecture. And the architecture we're using for this problem has 4 convolutional layers, a dense layer, and 1 output layer, where the output consists of 6 supernovae classes and 1 host class. And we were using 10,000 data points for each of these. So moving on to the results, very exciting results. So for the full sample, we were getting about 70% accuracy with the classifier that classifies 7 different categories. It's a lot higher when you're just classifying hosts and supernovae, where we're getting about 98% accuracy. But one thing, so this is the confusion matrix that correspond to it. So ideally, you would like this to be completely diagonal. So one thing you see is that the supernovae that have low brightness are being misclassified as hosts. So if we make a cut on the classifier, we can see that the results improve dramatically. Like this is almost all completely diagonal. This is one offset case, but let the numbers not fool you. The 100% here is not very representative because only 1 or 2 host galaxies have a high brightness. So this result is a huge improvement if you do make the cut. So we can also try to understand the performance better by the ROC curves. So ideally, in ROC curve, you would want this to be here because the idea is you have no false negatives. And you see that our classifier does a very, very good job. Um, and similarly, for PR curves, you want to be here because being here corresponds to having no false positives. So you see again that this reinforces the fact that our classifier is doing a very, very good job. We would like to note that once you do make the cut, there's a sort of trade-off between the number of points that you retain, because essentially you're cutting off some data points, and the purity of the sample that you want to get. So that just brings me to the conclusions. We see that there's a high accuracy um, in classification, and which is further increased if we make the hard cuts on the probable transients. We also see that if we make the sample more pure, it decreases the false positive rate and stops most of the hosts from being classified as transients, except that this one guy that somehow made it. So what are the future directions that we are looking at? So the first and immediate thing that we are working on is optimizing this network further, especially when we have 7 classes. And we want to improve from 70-80% that we have. Something we are working on right now is hyperparameter tuning, because, as I said, these networks learn on themselves, but you do need to supply some initial conditions that are called hyperparameters. So we're trying to fine tune them. Something that I'm very excited about is using ScoreCam. So ScoreCam essentially generates a heat map of what features the network is learning on, right? So this will basically allows us to see what machine is learning on, and we can compare them to the traditional practices that we saw here. And lastly, right now, so far, we have been using 1D fluxes to train on. But going ahead, we want to try 2D classification. So rather than training on individual fluxes, we train on this image. The only problem with that is there's a lot of white space. So the classifier will learn on basically no data here. So we are exploring sort of chopping these images and co-editing them in such a way that we minimize the white space, but also it doesn't confuse the classifier as much. So these are the future directions. Um, I would like to acknowledge the support from the Department of Energy and of High Energy Physics and the University of Rochester DESI group that has been um, very useful with their comments on the survey. And if you have any questions, please feel free to reach out. Thank you very much for being here.